In 2011, 4 papers were published simultaneously in the Astrophysical Journal. A team of NASA scientists, veterans of the mission that measured the temperature of the universe to 4 decimal places, had pointed the most precisely calibrated radio instrument ever built at the sky. The number they got back was 6 times higher than every known source of radio emission in the observable universe combined. That result was peer-reviewed, it was independently confirmed, and then it was quietly filed away. 2 workshops have been held. At the first, the attending astrophysicists voted unanimously that this represents a major outstanding question. Then they went home. 11 explanations have been proposed. Every single one has failed. Tonight we are going from the balloon flight that found this signal, through the 11 doors that closed, one by one, through the cosmic dawn detection that briefly looked like the answer before it fell apart, to the implication nobody wants to say out loud. Get comfortable. Subscribe or join if you haven't, and if you want deeper explorations across space, physics, and the questions that never get press releases, you can find more on Patreon. Stay to the end, because where this leads, the realization that even the visible universe is not accounted for is not something you walk away from easily. Let's start where it started. Right now, as you are listening to this, a signal is passing through your body. It is a radio signal. It is coming from every direction simultaneously, with equal intensity, no matter where on the sky you point a receiver. It has no identified source. It was measured in 2006 by a team of NASA scientists who launched the most precisely calibrated radio instrument in human history to the edge of the atmosphere. And what they found when they pointed it at the sky was not what they were looking for. They were searching for the faint thermal whisper of the first stars that ever ignited in the universe. A signal so weak, it would require cooling the entire instrument to 2.7 Kelvin, nearly absolute zero, just to separate it from the noise. What they heard instead was 6 times louder than every known radio source in the observable universe combined. Every galaxy, every quasar, every supernova remnant, every active galactic nucleus, every magnetar, every pulsar, everything that has ever produced a radio wave in 13.8 billion years of cosmic history, all of it together, accounts for less than 1/5 of what is actually there. That was 19 years ago, and to this day, not a single physicist on Earth can tell you what is producing it. I spent an unreasonable amount of time reading about this. Weeks, primary papers, workshop proceedings, instrument design documents, source count analyses, spectral modeling studies, and every proposed explanation I could find in the refereed literature and on the archive preprint server. And I want to be precise about what I am claiming, because precision matters here. This is not a marginal anomaly. This is not a subtle discrepancy buried in error bars that could dissolve with a recalibration or a revised foreground model. This is the electromagnetic equivalent of walking into your house and finding 6 times more furniture than you own, arranged in a pattern consistent with a specific manufacturing process. In a house whose inventory was supposed to be the one part of the universe we had fully accounted for. Something is producing an ocean of radio energy that fills the entire observable universe, isotropically, and that something does not correspond to any object, any population, any process, any particle, or any mechanism that currently exists in our physical models. It is real. It is confirmed. It is published across 4 simultaneous papers in the Astrophysical Journal. It has been independently verified by a completely separate instrument in New Mexico, operating at completely different frequencies. 2 international workshops have been convened specifically to address it, with participants from institutions across 3 continents. and you have almost certainly never heard of it. The reason you have never heard of it is not that it was debunked, not that it was retracted, not that the physics community quietly solved it while nobody was paying attention. The official conclusion from the most recent workshop held in Barolo, Italy in June 2022, and published in the publications of the Astronomical Society of the Pacific by Jack Single and colleagues, describes this signal as, and I am quoting directly, the least well-understood electromagnetic background at present. That is the careful, diplomatic workshop report version. 5 years earlier, the first workshop had used stronger language, calling it by far the least well-understood photon background. They dropped the by far, not because the situation improved, because the community learned to live with the discomfort. And here is where this becomes something more than an interesting puzzle in observational radio astronomy. Because the spectrum of this signal, its precise shape as you move across different radio frequencies, tells you what kind of physical process must be producing it. The spectrum is consistent with synchrotron radiation. I need to explain what that is, because it is the key to understanding why this signal is so disturbing. Synchrotron radiation is produced when charged particles, typically electrons, are accelerated to speeds approaching the speed of light and then forced to spiral through a magnetic field. The magnetic field bends the electron's path into a helix. As the electron curves, it emits electromagnetic radiation. The faster the electron moves, the shorter the wavelength of the radiation and the more intense the emission. A population of relativistic electrons with a range of energies spiraling through a magnetic field of a given strength will produce a broadband spectrum that follows a specific mathematical shape, a power law, where the brightness at any frequency is proportional to the frequency raised to some constant exponent. The value of that exponent, the spectral index, encodes the energy distribution of the electrons. Different sources of relativistic electrons produce different energy distributions and therefore different spectral indices. The spectral index is a fingerprint. The fingerprint of the Araki 2 excess is unmistakable. It follows a power law with spectral index -2, 0.62 plus or minus 0.04. That is the signature of synchrotron radiation from a population of relativistic electrons with a specific energy distribution, embedded in magnetic fields of a specific characteristic strength. This is not abstract. This is a supply list. You need electrons moving at nearly the speed of light. You need magnetic fields to make them spiral. You need a mechanism to accelerate them and sustain them against energy losses from the radiation they emit. And you need enough of all three, distributed uniformly enough across the entire sky to produce an isotropic signal that outshines every galaxy in the observable universe. The spectrum is telling us the ingredients, and we cannot find the kitchen. Before I take you through why every attempt to find it has failed, you need to understand who built the instrument that heard this signal, because the credibility of these people is not incidental. It is the reason this result cannot be dismissed as instrumental error or sloppy analysis. The instrument was called Aracade 2. The acronym stands for Absolute Radiometer for Cosmology, Astrophysics, and Diffuse Emission. It was conceived and built at NASA's Goddard Space Flight Center in Greenbelt, Maryland, under the leadership of a physicist named Alan Kogut. Kogut is a veteran of the COBE mission, the Cosmic Background Explorer, the satellite that produced the foundational measurements on which modern observational cosmology rests. In 1992, COBE's differential microwave radiometer team, which Kogut was part of, detected the first temperature anisotropies in the cosmic microwave background, the tiny ripples in the afterglow of the Big Bang. Roughly 1 part in 100,000 variations that seeded the gravitational collapse of matter into every galaxy, every star, every planet in the observable universe. That measurement, combined with the COBE SARAS measurement of the CMB blackbody spectrum, contributed to the 2006 Nobel Prize in Physics, awarded to John Mather and George Smoot. Kogut was on the team. He was in the room when the data came in. He knows, at a visceral level, what it means to make a measurement that changes how humans understand the universe they inhabit. And the scientist who worked alongside Kogut on Arrowcade 2 knew something even more specific. Dale Fixsen, at the University of Maryland, with a long-standing affiliation at Goddard, is the lead author of the paper that established the temperature of the cosmic microwave background to 4 decimal places. Fixsen et al., 1996, Astrophysical Journal, volume 473, page 576. That paper reported the CMB temperature as 2.728 plus or minus 0.004 Kelvin. Measured by COBE's SARAS instrument, the CMB blackbody spectrum is the most perfect Planckian blackbody ever observed in nature. The residuals from a perfect blackbody fit are less than 50 parts per million. No laboratory source on Earth produces a blackbody that clean. And the man who made that measurement, the man who literally measured the temperature of the entire universe to a precision of 4 millikelvin, is the same man who reported what is now sitting on top of that measurement, unexplained. When these two scientists, these two specific humans, tell you that they have found a radio signal that cannot be accounted for by any known source in the universe, the appropriate scientific response is not casual dismissal. It is not, well, maybe they made an error. It is to pay very close attention. The reason Arrowcade 2 succeeded where previous instruments had failed has everything to do with Fixsen and Kogut's decades of experience on COBE. They knew, better than anyone, that absolute radiometry, measuring the exact brightness of the sky as opposed to measuring relative differences between patches of it, is the hardest type of measurement in observational astronomy. Every single dish radio survey conducted before Arrowcade 2 had calibration uncertainties of 5 to 20%. That is an enormous window. The excess that Arrowcade 2 discovered amounts to roughly 80% of the extragalactic radio background. If your calibration is uncertain by even 10%, the excess hides inside your own error bars. You cannot see it. This is almost certainly why nobody found it sooner. Not because they were not looking, not because they were incompetent, because their instruments were simply not sharp enough. The anomaly was always there. It was the precision that was missing. Arrowcade 2 was designed to provide that precision. The instrument carries 7 double-null radiometers, covering frequencies from 3 to 90 GHz. A 3.15 GHz channel was added specifically for the 2006 flight. The entire apparatus is submerged in an open aperture duar filled with roughly 2,500 liters of liquid helium, cooling the instrument to approximately 2.7 Kelvin. That temperature was chosen for a specific and elegant reason. The cosmic microwave background has a temperature of 2.725 Kelvin. By cooling the instrument to match the CMB, they eliminated the instrument's own thermal self-emission from the measurement. The radiometers cannot hear themselves. They are thermally invisible against the signal they are trying to measure. Each radiometer alternately views the sky and an external full-aperture cryogenic blackbody calibrator, a carefully engineered surface built from 298 steel cast-on aluminum absorber cones that absorb and re-emit radiation as a perfect blackbody at a precisely known temperature. The rapid switching between sky and calibrator, dozens of cycles during the flight, allows each sky measurement to be referenced against a known standard on timescales short enough to cancel instrumental drifts. The gondola rotates at 0.6 revolutions per minute, so the radiometer beams sweep a 60-degree circle on the sky, 30 degrees from the zenith, providing multiple independent measurements at different sky positions. The result was an instrument with a gain error of less than 0.03% and a zero-level error of less than 10 millikelvin. That is roughly 100 times more precise than any previous single-dish radio survey. When this instrument reports an excess of 54 millikelvin at 3.3 gigahertz, that measurement is not sitting inside the error bars. It is sitting 5 standard deviations above them. There was also a first flight, July 2005, Palestine, Texas. The balloon separated prematurely before the instrument reached altitude. No science data was collected. The gondola came down. The instrument was recovered. Kogut and his team inspected it, rebuilt what needed rebuilding, waited another year, and shipped it back to the same balloon facility for a second attempt. I mention this because it matters for understanding the people involved. These are not scientists who got lucky on their first try. They failed, recovered, rebuilt, and tried again. The second flight, the one that produced the measurement that has confounded astrophysics for nearly 2 decades, was not their first attempt. It was their second chance. That second chance launched at 1:15 UTC on July 22, 2006, from NASA's Columbia Scientific Balloon Facility in Palestine, Texas. A 29.47 million cubic foot zero-pressure balloon carried the payload to 122,200 feet, roughly 37 kilometers above the Earth's surface, above 99.5% of the atmosphere, and almost all of its radio interference. The gondola hung 64 meters below the balloon train on its cable, rotating slowly, sweeping the sky. The flight lasted 7 hours and 51 minutes. The useful data came from 6 of the 7 channels. The 5 gigahertz switch failed in flight. At 8:21 UTC, the flight was terminated. The gondola parachuted down and was recovered 40 miles southeast of Fort Stockton, Texas, in the scrubby ranchland of West Texas. And when the team processed the data, subtracting the known contribution of the cosmic microwave background and modeling and subtracting the Milky Way's foreground emission, what remained was not what any model predicted. Let me be explicit about what they expected, because the gap between expectation and observation is the entire story. Radio astronomy has been mapping the sky since Carl Yansky first detected radio emission from the center of the Milky Way using a rotating antenna at Bell Telephone Laboratories in Holmdel, New Jersey in 1932. In the 94 years since, we have conducted thousands of radio surveys, built telescopes spanning hundreds of meters, linked arrays of antennas across continents using interferometry, and catalogued millions of individual radio sources. The history of radio source counting is one of the most meticulous accounting projects in all of observational science. You point a radio telescope at a patch of sky. You count every source you can detect. You measure how bright each one is. You build a number count distribution, plotting how many sources exist at each brightness level. You extrapolate the distribution to flux densities below your detection threshold, using well-established statistical models derived from galaxy evolution theory. You integrate. The result is a predicted sky temperature, the total radio brightness that all extragalactic sources, known and extrapolated, should contribute. At 3.3 gigahertz, the prediction was roughly 10 to 15 millikelvin. At 1.4 gigahertz, roughly 100 millikelvin. These are small numbers. The extragalactic radio sky was supposed to be a dim, well-behaved background, much fainter than the CMB or the galactic foreground, a whisper beneath the shouting of our own galaxy. This prediction was not speculative. It was based on decades of painstaking radio surveys, on the Condon and Mitchell source counts, on the Hopkins VLA surveys, on the FIRST and NVSS surveys that catalogued millions of radio sources across the northern sky. It was the accumulated knowledge of an entire field, validated against multiple independent datasets, cross-checked across multiple frequencies. The prediction was solid. The whisper was a roar. At 3.3 GHz, the residual after subtracting CMB and galactic foreground was 54 plus or minus 6 millikelvin, roughly 4 to 5 times the predicted contribution from all known sources. And the excess was not just at one frequency. When Fixsen combined the Arcade 2 measurement with existing absolutely calibrated radio surveys at 22, 45, 408, and 1420 MHz, the excess traced a single, clean, unbroken power law across the entire radio spectrum. Temperature equals 1.19 plus or minus 0.14 Kelvin times frequency in gigahertz raised to the power negative 2.62 plus or minus 0.04. A synchrotron power law, the same spectral shape, the same index, the same physics, at every frequency where it has been checked, from 22 MHz to 10 GHz, across more than 2 decades of the electromagnetic spectrum. And the lower you go in frequency, the louder it gets. That is what a negative power law index means physically. At 3 GHz, the excess is tens of millikelvin. At 1.4 GHz, it is hundreds of millikelvin. At 40 MHz, it dominates the sky. The universe gets louder the deeper you listen. The results were announced publicly at the 213th meeting of the American Astronomical Society in Long Beach, California, on January 7, 2009, by Michael Seifert of NASA's Jet Propulsion Laboratory and Kogut. Seifert is now the US project scientist for the Euclid Dark Energy mission at JPL. He is not a junior researcher making a splash. He is a senior NASA scientist who has staked his professional credibility on the measurement. After peer review, 4 papers were published simultaneously in the Astrophysical Journal on June 10, 2011. Fixsen et al., APJ, Volume 734, Article 5, reporting the measurement itself. Kogut et al., APJ 734, Article 4, presenting the galactic emission model used for foreground subtraction. Seifert et al., APJ 734, Article 6, interpreting the result and systematically ruling out known source populations. And Single et al., APJ 730, Article 138, describing the Arcade 2 instrument in exhaustive technical detail. 4 papers, 4 simultaneous publications, the scientific equivalent of putting your entire hand on the table and daring anyone to find a flaw. Kogut told NASA's press office that the universe really threw them a curve instead of the faint signal they hoped to find. Here was this booming noise, 6 times louder than anyone had predicted. Seifert told NBC News that they really did not know what it was, that this is what makes science so exciting. You start out on a path to measure something, in this case the heat from the very first stars, and you run into something else entirely, some unexplained phenomenon. And Fixsen offered the line that has since become the defining quote of the space roar. He said there do not appear to be enough radio galaxies to account for the signal Arcade detected. You would have to pack them into the universe like sardines. There would not be any space left between one galaxy and the next. That phrase, space roar, is worth pausing on. It is not a technical term. You will not find it in any peer-reviewed paper. The refereed literature calls it the Arcade 2 excess, or more formally, the radio synchrotron background, abbreviated RSB. Space Raw is a journalistic invention, a catchphrase that emerged from NASA's January 2009 press release, which described cosmic radio noise that booms 6 times louder than expected. Space.com picked it up. NBC ran with it. Gizmodo used it. SciShow used it. And the name stuck in popular culture even as the scientific community continued using the more precise terminology. I am using it here because it is evocative and because, for once, the journalistic instinct was correct. The signal is a roar. It is louder than everything else, and calling it a background makes it sound passive and unimportant, which it is not. What you need to understand about the period between the 2006 flight and the 2009 announcement is that the team did not rush to publication. They spent nearly 3 years checking their work, 3 years of reprocessing data, re-examining the calibration, testing alternative foreground models, looking for systematic errors, trying to make the excess go away. Because the first instinct of any good experimentalist who finds a result this large and this unexpected is not excitement. It is suspicion. Suspicion of their own instrument. Suspicion of their own data reduction pipeline. Suspicion that somewhere in the chain from sky to radiometer to computer to paper, an error crept in and produced a phantom signal. Kogut and Fixsen knew this better than anyone, because they had spent decades on COBE learning exactly how subtle instrumental systematics can masquerade as cosmic signals. COBE's legacy included not just groundbreaking discoveries, but a hard-won institutional memory of every way that an instrument can fool you. Reflections of the instrument structure, temperature gradients in the calibrator, side lobe pickup from the Earth or the Sun, ground loop interference in the electronics. Fixsen spent years calibrating COBE's SARAS instrument, learning every mode by which thermal emissions from the spacecraft itself could contaminate the astrophysical signal. He brought that paranoia, and I mean that as a compliment, to Arcade 2. Every systematic error he could conceive of was tested, bounded, and either corrected or shown to be negligible compared to the excess. And the excess remained through every test, through every alternative analysis, through 3 years of trying to kill it. It sat there, 54 plus or minus 6 millikelvin, at 3.3 gigahertz, following its clean power law, refusing to be explained away. When the team finally published, it was not because they were confident the excess was real. It was because they had exhausted every argument for it being fake. That is an important distinction. They did not prove the excess exists. They proved they could not make it go away. And in experimental physics, when you have spent 3 years trying to kill a result, and the result survives, you publish it and let the community try. The community has been trying for the 14 years since publication. The result is still alive. But here is where it gets worse, because confirming the signal was measured correctly is only the first step. The second step is confirming it with a completely independent instrument. And that happened. In 2018, Jens Dowell and Greg Taylor at the University of New Mexico published a paper in the Astrophysical Journal Letters, volume 858, article L9, reporting a measurement of the absolute radio sky brightness at 40 to 80 megahertz using LWA-1, the first station of the long wavelength array in central New Mexico. LWA-1 is a completely different kind of instrument from Arcade 2. It is a ground-based phased array, not a balloon-borne cryogenic radiometer. It operates at frequencies 30 to 50 times lower than Arcade 2's primary channel. It uses a completely different calibration strategy based on known radio sources and beam modeling rather than cryogenic blackbody references. And it was built by a completely different team for completely different science goals. Dowell and Taylor measured the absolute zero level of the radio sky between 40 and 80 megahertz. The ARA-K2 power law, extrapolated from 3.3 gigahertz down to these frequencies, predicts a specific excess brightness at the LWA band. The LWA measurement matches the spectral index measured by LWA1 is negative 2.58, plus or minus 0.05, consistent within errors with the ARA-K2 value of negative 2.62 plus or minus 0.04. Two different instruments, two different teams, two different decades of the electromagnetic spectrum, two different calibration philosophies, the same signal. I want to pause on this because independent confirmation is the gold standard in observational science, and too many anomalies fail to reach it. The history of astrophysics is littered with claimed detections that vanished under scrutiny, with instrumental artifacts masquerading as cosmic signals, with results that could not be reproduced by anyone other than the original team. The BIC EK2 gravitational wave claim in 2014, which turned out to be galactic dust. The superluminal neutrino claim from Opera in 2011, which turned out to be a loose fiber optic cable. When a result survives independent confirmation by a completely different instrument using a completely different technique, you stop asking whether the result is real and start asking what it means. The space roar passed that threshold in 2018, and yet the broader reception of this result has been strangely muted. When the original ARA-K2 results were announced in January 2009, they generated a burst of media coverage. Space.com ran it, NBC covered it, Discover magazine included it in their Top 100 Stories of 2009. New Scientist featured it. NASA issued a formal press release with quotes from the team members. The phrase space roar entered the popular vocabulary. For about a week, it was news. Then it faded, and what replaced the coverage was not a sustained investigation, but silence. The 4 APJ papers were published in June 2011 without a media cycle. The LWA1 confirmation in 2018 generated almost no popular coverage at all. A result that is, in quantitative terms, one of the largest unexplained discrepancies in observational astrophysics, a factor of 5 to 6 between prediction and measurement, got roughly the same amount of sustained public attention as a moderately interesting exoplanet discovery. Part of this is a problem of narrative. The space roar does not have a protagonist. It does not have a villain. It does not have a resolution. It does not fit into the triumphant arc of scientists discover something amazing, because the discovery is not amazing in the way that people expect amazing to feel. It is not a new planet. It is not a detected gravitational wave. It is not a photograph of a black hole. It is an accounting discrepancy, a number that does not match. And accounting discrepancies, no matter how large, do not photograph well. You cannot put a photon budget on the cover of a magazine. But here is what I keep coming back to: the size of the discrepancy. 5 to 6 times. That is not a rounding error that might go away with better measurements. That is a measurement of 65 millikelvin, where 13 was expected. That is a universe-filling signal that overpowers the combined emission of every known radio source by a factor that would be considered catastrophic in any other branch of observational science. If the cosmic microwave background had been measured at 5 times the predicted temperature, it would have been the biggest story in physics. If the Hubble constant were off by a factor of 5, Cosmology would have shut down and rebuilt from scratch. The radio excess is off by the same factor, and the response has been 2 workshops in 19 years. And that signal, to a first approximation, is everywhere and nowhere. Isotropic, meaning it comes equally from all directions, without hot spots or cold spots, without a preferred direction, without any obvious correlation with known large-scale structures. Just a uniform bath of radio photons filling the entire observable universe, louder than every known source combined, following a clean synchrotron power law, and refusing to be explained. I need to stop here and make sure something lands properly, because I think the strangeness of this situation gets normalized if you move too quickly past it. Every other electromagnetic background in the universe has been accounted for. Let me walk you through what that means, because it is the context that makes the radio anomaly so disturbing. Start with the cosmic microwave background, the oldest light in the universe. It was released roughly 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral atoms, and the photons that had been trapped by constant scattering of free electrons suddenly found themselves in a transparent universe and streamed outward in every direction. That radiation has been cooling with the expansion of the cosmos ever since, and today it fills every cubic centimeter of space as a nearly perfect black body at 2.725 Kelvin. We know what produced it. We know when it was produced. We know its temperature to 4 decimal places. The accounting is closed. Now the cosmic infrared background. This is the integrated infrared emission from every dusty galaxy in the history of the universe. When stars form inside clouds of gas and dust, much of the ultraviolet and visible light they emit is absorbed by the surrounding dust and re-radiated at longer wavelengths in the infrared. The cosmic infrared background is the accumulated glow of all that reprocessed starlight from every galaxy at every epoch, summed over the entire line of sight. We have measured it with instruments like COBE's Derby detector, Herschel, Spitzer, and Planck. We have compared it to the integrated emission from galaxy surveys, adding up the infrared contributions from billions of individually detected galaxies. The totals match. The accounting is closed. The extragalactic background light in the optical and ultraviolet. This is the accumulated starlight from every star in every galaxy that has ever existed, minus what was absorbed by dust. We have measured it through direct photometry and through indirect methods, using gamma-ray observations of distant blazars, whose spectra are attenuated by pair production interactions with background photons. The measurements from different techniques converge. The galaxy surveys account for the observed level. The accounting is closed. The cosmic X-ray background, discovered in 1962 by Riccardo Giacconi, who later won the 2002 Nobel Prize for founding X-ray astronomy. This diffuse X-ray glow was eventually resolved into the emission of millions of active galactic nuclei, supermassive black holes, at the centers of galaxies whose accretion disks produce copious X-rays. Deep surveys with the Chandra X-ray Observatory and XMM Newton have resolved 80 to 90% of the background into individual sources. The remaining fraction is consistent with models of unresolved, faint, active nuclei. The accounting is closed. The extragalactic gamma-ray background, measured by the Fermi Gamma-Ray Space Telescope's Large Area Telescope, it is dominated by blazars, active galactic nuclei whose relativistic jets happen to point roughly toward Earth, amplifying their emission through relativistic beaming. Source count analyses and luminosity function models account for the observed level within the measurement uncertainties. The accounting is closed. 5 backgrounds, 5 frequency bands spanning 14 decades of the electromagnetic spectrum, from microwave through gamma ray. 5 successful audits where the photons observed match the photons predicted from known sources. And then there is the radio band. And the radio band does not close. The discrepancy is not 10%. It is not 50%. It is 400 to 500%. The measured radio background is 5 to 6 times brighter than everything we know about can produce. To put that in terms that might make the scale visceral, imagine you are an accountant auditing a company with 6 divisions. 5 divisions have books that balance perfectly. Revenue matches expenses. Every transaction traces to a source. Every dollar is accounted for. Then you open a ledger for the 6th division and find that the revenue is 6 times higher than every transaction you can identify. Not a rounding error. Not a missing entry. 6 times more money flowing in than you can attribute to any customer, any contract, any product line. You would not shrug and file the report. You would tear the accounting apart. And if, after 19 years of forensic analysis, every accountant you hired confirmed the numbers, and none of them could find the source of the extra revenue, you would begin to suspect that your understanding of how the business operates is fundamentally wrong. That is where astrophysics is with the radio background. 5 out of 6 electromagnetic backgrounds balance. The 6th is off by a factor of 6, and nobody can find the extra entry. And here is a detail I want you to carry, because it is going to become heavier the further we go. The Aracade-2 instrument was not just looking for any old signal. It was designed, specifically and deliberately, to measure the radio emission from the first generation of stars in the universe. Population 3 stars. These are the theoretical first stellar objects, predicted by every model of cosmic structure formation, but never directly observed. They are believed to have been enormous, perhaps hundreds of times the mass of our Sun, burning so hot and so briefly that they fused primordial hydrogen and helium into the first heavier elements: carbon, nitrogen, oxygen, iron, the atoms that would eventually become the raw material for rocky planets, liquid water, organic chemistry, DNA, and everything made of DNA. Every heavy atom in your body was forged inside a star, and the very first of those stars, the ones that began the chain, left a faint radio signature in the cosmic background, a subtle thermal excess above the CMB, produced by the free emission of the hot gas surrounding them. Aracade-2 was built to find that signature, to hear the echo of the moment the universe learned to make chemistry. And something else was louder. The first stars tried to leave a message, and something drowned it out. I want you to hold that image, because we are going to come back to it at the end. Now I want to take you through the explanations that were tried and failed, because the pattern of failures is itself the most important part of this story. It is not that we tried one idea and it did not work and we need another idea. It is that we tried every idea the field could generate, and none of them work, and the failure modes are all different. Each door closes for its own specific reason, and those reasons, taken together, constrain the solution space so tightly that what remains is almost nothing. The first attempt was the most obvious and the most boring. Maybe we missed some radio sources. Maybe there are faint galaxies below our survey limits. Maybe if we just looked harder, with more sensitive instruments, we would find them. This is the astrophysicist's version of assuming you miscounted the silverware before calling the police. James Condon, one of the most respected figures in radio astronomy, the man who literally co-authored the standard textbook on radio techniques, attacked this question in 2012. He and his colleagues published in the Astrophysical Journal, Volume 758, Article 23, using a P-D confusion analysis on the DEE P23 GHz survey. PD analysis is a statistical technique that extracts information about sources too faint to resolve individually by studying the pixel-to-pixel brightness fluctuations in a deep radio image. If a hidden population of ultra-faint sources exists, it leaves a statistical fingerprint in the noise. The noise was clean. The faint sources were not there. Condon found that the total sky temperature from all discrete radio sources, resolved and unresolved, at 3 GHz is approximately 13 plus or minus 1.3 millikelvin. The Arcade-2 excess at the same frequency is about 50 millikelvin above that. To close the gap with point sources, you would need a population roughly 5,000 times denser than the PD data allow, with individual source flux densities peaking below 0.5 nanojansky. For perspective, the faintest radio sources ever detected by any telescope, using hundreds of hours of integration on instruments like the Carl G. Jansky Very Large Array, are in the microjansky range. A nanojansky is 1,000 times fainter. Half a nanojansky is fainter still. No model of galaxy formation, no active galactic nucleus luminosity function, no star formation rate density history produces a population like this. The sources that would be needed do not exist in any theoretical framework, and the geometric constraint is even more devastating than the statistical one. Fixsen's sardine line is not hyperbole. Condon calculated explicitly that to produce the observed excess from discrete sources, those sources would need angular cross-sections so large and so numerous that they would tile the entire celestial sphere with zero gaps. Every line of sight from Earth would intersect a radio source. There would be no empty sky. And we know, from surveys at every other wavelength, infrared, optical, ultraviolet, X-ray, that the actual density of galaxies is nowhere near this. The sky has gaps, lots of them. The faint source explanation is not just unlikely, it is geometrically excluded. I want to pause here and make sure the scale of this registers, because numbers this extreme tend to slide off the brain without leaving a mark. When I say the known sources produce 13 millikelvin and the measurement is 65 millikelvin, those numbers are abstract. Let me make them concrete. Imagine you are a city planner. You have mapped every street light in a city. You know the wattage of each one. You have a satellite photograph of the city at night, and you can see how bright each street is. You add up the wattage of every street light, and you predict how much total light the city should emit. Then you look at the satellite photo, and the city is 6 times brighter than every street light can account for. Not twice as bright, not 3 times, 6 times. That is the space roar. Something is lighting up the radio sky with 6 times more energy than every radio streetlight in the cosmos. And there are no extra streetlights. You have checked. You have sent someone to every street. The extra light has no lamps. Now imagine the city planner trying to explain this to the mayor. The mayor would ask reasonable questions. Did you miss some streetlights? No. We used the most sensitive detector ever built. We checked for streetlights too dim to see individually, using statistical methods. They are not there. Could it be light from another city? No. The excess is everywhere, not concentrated in any direction. Could it be the moon? No. The spectral profile does not match moonlight. Could it be something we have never seen before? A kind of street light we do not have a category for? That is the question we cannot answer, because we have tried 11 different kinds of hypothetical streetlights, and none of them work. That is where astrophysics has been for 19 years, looking at a city that is 6 times brighter than its streetlights and running out of ideas for where the light comes from. But that was only the most boring explanation. When the boring answer fails in science, the interesting answers take the stage. And this is where the story enters a phase that I find genuinely unsettling. Not because any single failed explanation is disturbing on its own, but because the accumulation of failures creates a pattern. Each candidate brings a different piece of physics. Each fails for a different reason. And the specificity of the failures, the way each one closes a different door, starts to feel less like a series of near misses and more like the universe systematically refusing to give up its secret. The first exotic candidate was dark matter annihilation. In December 2011, Nicolau Fornengo, Roberto Lineros, Marco Regis, and Marco Tauso at the University of Turin published a paper in Physical Review Letters, Volume 107, Article 271. 302. The proposal was elegant in the way that theoretical physics proposals often are, when they connect 2 unsolved problems simultaneously. Dark matter constitutes roughly 27% of the total mass energy of the universe. It forms enormous, diffuse halos around galaxies, extending far beyond the visible edges of the galactic disk. If dark matter consists of weakly interacting massive particles, WIMPs, in the mass range of 5 to 50 gigaelectronvolts, and if those WIMPs can annihilate when they collide with each other, converting their rest mass into energy in the form of showers of secondary particles, then among those secondary particles would be relativistic electrons and positrons. Those electrons would spiral through the magnetic fields of the dark matter halos and emit synchrotron radiation at radio frequencies. The appeal is obvious. Dark matter is everywhere. Its halos are enormous, filling exactly the kind of diffuse, extended volume where you need the emission to be. And when Fornengo and colleagues ran the numbers, the total brightness of the predicted synchrotron signal integrated over all dark matter halos in the observable universe roughly matched the Arcade 2XS. The amplitude was right. The spectral shape was wrong. The observed power law index of the Arcade 2XS is negative 2.62. The spectral shape predicted by WIMP annihilation, after accounting for the energy spectrum of the secondary electrons, the magnetic field profiles of dark matter halos, and the energy losses from inverse Compton scattering off cosmic microwave background photons, does not reproduce this index. The predicted spectrum curves in the wrong places. It is too flat at some frequencies and too steep at others. Close is not good enough in spectral analysis. The spectral index is the fingerprint. A fingerprint that almost matches is still a mismatch, and the multi-wavelength counterparts sealed the case. Dan Hooper and colleagues at Fermilab, in a 2012 paper, HarkCiv 1 203.3547, examined what a dark matter annihilation scenario bright enough to produce the radio excess would predict at other wavelengths. The same cascades that produce relativistic electrons also produce gamma rays. The Fermi Large Area Telescope should see them. It does not. The dark matter halos of local group dwarf spheroidal galaxies, which are dominated by dark matter and have weak magnetic fields, should glow at both radio and gamma ray frequencies. They do not glow at either. Klein and Vincent in 2013 pushed the constraints further. The annihilating WIMP scenario is caught in a crossfire. Radio data demand more emission. Gamma ray data forbid it. You cannot satisfy both. The verdict is clear, and it has stood for over a decade. Dark matter annihilation can produce approximately the right total brightness of radio emission, but the spectral fingerprint does not match. and the predicted counterparts at other wavelengths are missing. The amplitude is right. The identity is not. That is not a subtle discrepancy. That is a fundamental mismatch between what the theory predicts and what the sky actually looks like. And I want you to hold something in your mind here, because it is going to become important later. The signal has a definite, measured, specific spectral fingerprint. It looks like synchrotron radiation from a population of relativistic electrons with a particular energy distribution. That fingerprint constrains the source, not just in terms of what it is, but in terms of what it is not. And so far, it is not anything we know about. The second exotic candidate was primordial black holes. And I want to give you the number from this one because the number itself tells a story about the scale of the problem. Primordial black holes are theoretical objects that might have formed in the first fraction of a second after the Big Bang from extreme density fluctuations. Stephen Hawking demonstrated in the 1970s that black holes are not perfectly black. Through a quantum mechanical process involving virtual particle pairs at the event horizon, black holes slowly radiate energy, and the smaller the black hole, the hotter the radiation. A primordial black hole with a mass around 10 to the 12th to 10 to the 14th kilograms would be small enough and hot enough to be actively evaporating right now, emitting particles across a range of energies. Could the accumulated Hawking radiation from a cosmological population of these objects account for the Aracade-2 excess? Ketan Mittal and Girish Kulkarni at the Tata Institute of Fundamental Research in Mumbai calculated the answer and published it in the monthly notices of the Royal Astronomical Society, Volume 510, page 4992, in March 2022. The total radio brightness from Hawking radiation, even assuming that 100% of the dark matter in the universe consists of primordial black holes at the mass range where evaporation is most intense, is approximately 10 to the negative 46th power Kelvin. Let me translate that. The observed excess is roughly 1 Kelvin at low frequencies. The predicted contribution from primordial black hole evaporation is 0.000, and then 43 more zeros, and then a 1 Kelvin, 46 orders of magnitude too faint. If the Aracade-2 excess were the distance from Earth to the Sun, 150 million kilometers, the Hawking radiation contribution would be smaller than the diameter of a hydrogen atom. This explanation does not fail gracefully. It fails catastrophically. The third candidate was more interesting and more subtle, and it came from a group of theorists whose physics I respect even though the result ultimately falls short. Yuri Keshet at Ben-Gurion University of the Negev, Eli Waxman at the Weizmann Institute of Science, and Avi Loeb at Harvard published in 2004 in the Astrophysical Journal, Volume 617, page 281, a model in which the intergalactic medium itself produces synchrotron radiation through a well-established plasma physics mechanism. Their argument runs as follows. The large-scale structure of the universe, the cosmic web of filaments, nodes, and voids, assembled over billions of years through gravitational collapse, as matter fell into the deep gravitational wells of galaxy clusters and superclusters. The infalling gas accelerated to velocities of hundreds to thousands of kilometers per second. At the boundaries of these clusters, where the fast-moving infalling gas slams into the hot, dense intracluster medium, enormous accretion shocks form, the virial shocks. These shocks are a standard prediction of structure formation cosmology. They have been indirectly observed through X-ray and radio signatures of galaxy clusters. And they do what shocks do in ionized, magnetized gas. They accelerate charged particles to relativistic energies through the Fermi acceleration mechanism. The relativistic electrons produced by virial shocks then spiral through whatever magnetic field exists in the intergalactic medium and emit synchrotron radiation. The physics is real. The shocks exist. The acceleration mechanism operates. And Keshet, Waxman, and Loeb showed that the resulting synchrotron emission could contribute a meaningful fraction of the cosmic radio background, potentially up to a few tens of % at frequencies below 500 MHz. That is not negligible. It is a real astrophysical contribution, but a few tens of % is not 500%. The intergalactic shock mechanism explains perhaps 10 to 15% of the observed excess, leaving 85 to 90% unaccounted for. You cannot build a bridge that covers 10% of the river and call the crossing solved. And there is a more fundamental constraint. Relativistic electrons do not just emit synchrotron radiation, they also scatter photons. Specifically, in the intergalactic medium, they scatter cosmic microwave background photons to higher energies through a process called inverse Compton scattering. If enough relativistic electrons existed in intergalactic space to produce the observed radio excess via synchrotron emission, those same electrons would simultaneously produce an excess in the diffuse X-ray background through inverse Compton upscattering of CMB photons. Single and colleagues examined this in 2010 and found that the X-ray background sets a hard upper limit on the total content of relativistic electrons in intergalactic space. That limit is well below what the radio excess requires. The electrons cannot hide between galaxies because if they were there, the X-rays would give them away. Two independent observational constraints, radio and X-ray, pulling in opposite directions. There is no parameter space where both are satisfied. Keshet has continued to pursue this line of investigation. In 2023, he and colleagues used the Owens Valley Radio Observatory Long Wavelength Array to search for the predicted synchrotron emission from virial shocks around stacked galaxy clusters. The search is ongoing, but even if the emission is found, it cannot close the gap. The amplitude shortfall is structural. The mechanism contributes, but it does not dominate. And then there was the candidate that tried to make the entire problem disappear by arguing it was never really cosmic in the first place. In 2013, Ravi Subramanian of the Raman Research Institute in Bangalore, India, and Ramanath Kaushik of Washington University in St. Louis published a paper in the Astrophysical Journal, volume 776, article 42, that attempted something none of the previous explanations had tried. Instead of proposing a new source for the excess, they proposed that the excess does not exist. Their argument is that Kogut and colleagues used an oversimplified model of the Milky Way's own radio emission when performing their foreground subtraction, and that the supposed extragalactic excess is actually misattributed galactic emission that the model failed to capture. The technical heart of their critique is this. Kogut modeled the Milky Way's foreground radio emission as a plain, parallel slab. In this approximation, the galaxy is treated as a flat disk, and the radio brightness at any point on the sky depends primarily on the galactic latitude, following a cosecant of galactic latitude dependence. This is a standard approximation used in radio astronomy. But Subramanian and Kaushik argued that the real Milky Way has a structure the plain parallel model misses, a large, roughly spheroidal radio halo extending approximately 15 kiloparsecs from the galactic center. This halo, they claimed, would produce significant emission at high galactic latitudes, the very regions of the sky where a KD2 made its measurements. If the plain parallel model does not account for this halo emission, it will be subtracted incorrectly, leaving a residual that looks extragalactic but is actually local. This was the most dangerous challenge to the Arcade 2 result, not because it was exotic, not because it invoked new physics, but precisely because it was mundane. The most damaging criticism in experimental science is not that your result is wrong, it is that your subtraction is wrong. And foreground subtraction in radio astronomy is genuinely difficult, fraught with modeling assumptions and calibration uncertainties that can propagate in subtle ways. But the Subramanian-Kausic model makes a specific, testable prediction. If the Milky Way has a bright radio halo extending 15 kiloparsecs, then other spiral galaxies similar to the Milky Way should have similar halos, and those halos should be visible. Specifically, when you image an edge-on spiral galaxy in the radio band, the halo would make the galaxy appear fatter, thicker, perpendicular to its disk than it appears in optical light. The axial ratio, the ratio of a galaxy's apparent width to its height in radio images, should be measurably larger than the axial ratio in optical images. Jack Single tested this directly. In 2015, he and colleagues published in the Astrophysical Journal Letters, volume 799, article L10, a beautifully simple experiment. They stacked radio images of edge-on spiral galaxies, galaxies seen from the side so that any halo structure would be maximally visible, and compared their radio axial ratios to their optical axial ratios. The result was clear. The galaxies are as thin in radio as they are in optical. No extended radio halo was detected around any of the comparison spirals. The 15 kiloparsec radio envelope that the Subramanian-Kausic model requires does not appear to exist around any galaxy we can observe from the outside. If our own Milky Way had such a halo, it would be a unique outlier among spiral galaxies, and there is no known physical reason to expect that. The descent is not fully resolved. It remains a minority, but live position in the community. The 2022 workshop report acknowledges it without dismissing it. Cross-correlation analysis and ongoing observational tests continue to probe the question, but the weight of evidence from the isotropy of the signal, from the spectral consistency across 4 decades of frequency, from the independent LWA1 confirmation, and from the failure of the predicted galactic halo to appear around analogous spiral galaxies, favors the extragalactic interpretation. The majority of specialists treat the Arcade 2 excess as real and cosmic. So let me now lay out clearly where we stand after exhausting the first round of explanations, because the accumulation matters. Undercounted faint galaxies were geometrically excluded by the Condon PD analysis. Dark matter annihilation produces the correct amplitude but the wrong spectral fingerprint and is missing gamma-ray counterparts. Primordial black hole. Hawking radiation is 46 orders of magnitude too faint. Intergalactic shock synchrotron is a real mechanism, but an order of magnitude too weak and constrained by X-ray limits. The galactic radio halo artifact has a testable prediction that fails when compared to analogous spiral galaxies. Population 3 stars are ruled out by reionization constraints. Quark nugget dark matter, proposed by Lawson and Zhitnitsky, requires entirely ad hoc particle physics, with no independent support. Dark photons survive only in extremely narrow, fine-tuned parameter windows. Superconducting cosmic strings and sterile neutrino decay are both purely speculative, and the local bubble around our solar system cannot produce an isotropic monopole signal that looks the same from every direction. I want to count those for you because the counting matters. That is 11 proposed explanations, 11 mechanisms spanning particle physics, plasma astrophysics, galaxy evolution, galactic structure, dark matter phenomenology, and exotic Cosmology. Each one was proposed by credentialed scientists and published in refereed journals. Each one was evaluated against the data. Each one failed. Not the same failure. 11 different failures, 11 different doors, closing for 11 different reasons. And behind all of them, the same signal, sitting unmoved, following its clean synchrotron power law, coming from everywhere, matching nothing. I personally find the dark matter failure the most instructive, and here is why. The dark matter annihilation model did not fail because the physics was sloppy. It failed because the physics was precise. The spectral shape was wrong, not approximately wrong. Specifically wrong, the observed spectral index is negative 2.62. The synchrotron spectral index depends on the energy distribution of the radiating electrons, and the energy distribution from dark matter annihilation cascades does not produce that number. It produces a different number. And in synchrotron physics, the spectral index is not a free parameter you can adjust with a few knobs. It is a consequence of the electron population. Change the electron population, you change the spectral index. The signal is demanding a very specific population of electrons with a very specific energy distribution. And dark matter annihilation does not produce that population. What does this tell us? It tells us the signal is picky. It is not just an amorphous excess of radio energy sloshing around the cosmos. It has a shape, and that shape rules things out. It rules out dark matter. It rules out Hawking radiation. It rules out every source whose electron energy spectrum does not match a power law index of roughly 6.24, which is the electron spectral index implied by the observed radio spectral index of negative 2.62 through the standard synchrotron relation. The signal is telling us what it is made of with remarkable specificity. Relativistic electrons with a particular energy distribution, spiraling through magnetic fields of a particular characteristic strength. That is a supply list with quantities and specifications, and nobody can find the supplier. Let me push this one step further, because the supply list deserves to be examined in detail. Synchrotron radiation requires three things, no more, no less. First, relativistic electrons. These must have kinetic energies much larger than their rest mass energy of 511 kilo-electron volts. To produce radiation at the frequencies where the excess is observed, the electrons need energies of roughly a few hundred mega-electron volts to a few giga-electron volts, depending on the magnetic field strength. These are not exotic energies. Cosmic ray electrons at these energies are commonplace inside galaxies. They are produced by supernova shocks, by pulsar wind nebulae, by the jets of active galactic nuclei, but they are not common in intergalactic space, because the mechanisms that produce them are all localized to galaxies and their immediate environments. Between galaxies, in the voids and filaments that constitute most of the volume of the universe, there are no known mechanisms operating at scale to accelerate electrons to relativistic speeds. Second, magnetic fields. The electrons must be spiraling through fields strong enough to produce radiation at observable frequencies. In galaxies, magnetic fields are typically a few microgauss. In the intracluster medium, similar strengths have been measured, but in intergalactic space, the filaments and voids of the cosmic web, the magnetic field strength is largely unknown. Upper limits from Faraday rotation measures and CMB observations suggest fields of, at most, a few nanogauss, thousands of times weaker than inside galaxies. Producing significant synchrotron emission in such weak fields requires correspondingly more energetic electrons, which in turn requires more powerful acceleration mechanisms, which are even harder to locate in the vast empty spaces between galaxies. Third, a mechanism to accelerate the electrons and sustain them against energy losses. Relativistic electrons lose energy continuously. They radiate it away as synchrotron emission. They scatter CMB photons and lose energy through inverse Compton cooling. And both processes drain the electron energy on timescales of millions to hundreds of millions of years. Without continuous reacceleration, the electrons cool and the emission fades. Whatever is producing the space raw is not a one-time event. It requires a sustained, ongoing source of relativistic electrons, operating across cosmological volumes, replenishing them fast enough to overcome radiative losses. And no known mechanism does this. The signal is not cryptic. It is specific. It is telling us what the source must look like. And the source does not exist in our models, which means either our models are missing something or there is something in the universe we have never conceived of. And here is where this story takes a turn that nobody anticipated, because in the spring of 2018, while the space raw sat quietly in the literature, waiting for its 12th explanation, a completely different experiment, at a completely different frequency, in a completely different country, looking at a completely different phenomenon, produced a result that briefly, electrifyingly, looked like it might solve everything. The experiment was called EDGES, the experiment to detect the global epoch of reionization signature. And to understand why it mattered for the space raw, I need to take you to the beginning of time, or close to it. Roughly 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. This is the epoch of recombination, and it is the event that released the cosmic microwave background, the wall of photons that COBE and Fixsen and Kogut measured so precisely. After recombination, the universe entered what cosmologists call the Dark Ages, a period of roughly 100 million years during which there were no stars, no galaxies, no sources of light, except the slowly cooling CMB. The universe was filled with neutral hydrogen gas, cooling as the cosmos expanded, and nothing else. Then, roughly 180 million years after the Big Bang, the first stars ignited. These were not stars like our Sun. They were population 3 stars, massive, hot, short-lived monsters made entirely of hydrogen and helium, because heavier elements had not yet been forged. Their ultraviolet radiation flooded the surrounding hydrogen gas, and here is where the 21-centimeter physics becomes important. Neutral hydrogen has a subtle quantum mechanical property. The proton and electron each have spin, an intrinsic angular momentum. Those spins can be parallel, both pointing the same direction, or anti-parallel, pointing opposite directions. The parallel state has slightly more energy. When a hydrogen atom flips from parallel to anti-parallel, it emits a photon at a frequency of 1420.4 MHz, corresponding to a wavelength of roughly 21 centimeters. This is the hydrogen 21 centimeter line, one of the most important frequencies in all of radio astronomy. At cosmic dawn, the ultraviolet light from the first stars did something specific and important. It coupled the spin temperature of the hydrogen gas to the kinetic temperature of the gas itself through a mechanism called the Wothusen field effect. Before the first stars turned on, the spin temperature of the hydrogen was equal to the CMB temperature, and the hydrogen was invisible against the CMB at 21 centimeters. But once the first stars coupled the spin temperature to the gas kinetic temperature, and the gas was colder than the CMB because it had been cooling adiabatically as the universe expanded, the hydrogen gas began absorbing CMB photons at 21 centimeters. The absorption creates a dip, a trough, in the spectrum of the radio background, centered at the frequency corresponding to the redshifted 21 centimeter line from that epoch. The depth of that trough depends on two things: how cold the gas was and how bright the radio background behind it. Standard cosmology, using the known CMB temperature at redshift 17, approximately 51 Kelvin, and the known thermal history of the hydrogen gas, predicts a maximum absorption depth of about 230 millikelvin. The man who set out to measure this was Judd Bowman. Bowman earned his PhD in physics from MIT in 2007, studying under Alan Rogers, one of the pioneers of precision radio instrumentation. He joined Arizona State University and received NASA's Nancy Grace Roman Early Career Technology Fellowship in 2012. He is not a dramatic scientist. He does not give rousing public talks or write popular science books. He is the kind of physicist who spends years calibrating a single antenna, iterating on its design, deploying it in remote deserts, analyzing the systematics, wrestling with foregrounds that are 10,000 times brighter than the signal, and doing it again. The 21 centimeter absorption measurement from cosmic dawn is routinely described as one of the hardest measurements in all of observational science, not because the underlying physics is complex, but because the engineering demands are relentless and unforgiving. Edges consisted of a deceptively simple antenna, a small metal ground plane, roughly the size of a dining table, with a blade dipole above it, deployed in the Murchison Shire of Western Australia, one of the most radio-quiet locations on Earth. Hundreds of kilometers from the nearest cell tower, with no television transmitters and no airport radar anywhere nearby, just red desert soil, scrub brush, and the radio silence that the measurement requires. Bowman and his team, including Alan Rogers, Raoul Monsalve, Thomas Mosden, and Nivedita Mahesh, spent years calibrating the antenna's beam pattern, measuring the reflection coefficient of the ground beneath it, characterizing the electrical properties of the cables and connectors, and modeling the Milky Way's synchrotron foreground, which, at 78 megahertz, is roughly 10 to 15,000 times brighter than the signal they were looking for. Imagine trying to hear a whisper during a thunderstorm, where the thunder is not just loud, but has a frequency structure that overlaps with the whispers. That is the edges foreground problem. This is worth understanding in detail, because it explains why the edges measurement was so extraordinary and why its collapse was so painful. At 78 megahertz, the frequency where the cosmic dawn absorption should appear, the sky is not quiet. It is dominated by the Milky Way's own synchrotron emission, a bath of radio noise produced by cosmic ray electrons spiraling through the galactic magnetic field. At 78 megahertz, this galactic foreground has a brightness temperature of roughly 4,000 to 5,000 Kelvin, depending on the direction. The signal Bowman was searching for, the 21 centimeter absorption dip from cosmic dawn, was predicted to be at most a few hundred millikelvin deep, superimposed on that 4,000 Kelvin foreground. That is a signal to foreground ratio of roughly 1 to 20,000. Imagine trying to detect a half-degree temperature change on the surface of a blast furnace from across the room using a thermometer that is itself being heated by the furnace. The foreground subtraction problem is what makes 21 centimeter cosmology so fiendishly difficult. The foreground is not just bright, it is spectrally smooth, meaning it varies slowly and predictably with frequency, following a power law. The absorption signal is also spectrally smooth, but it has a specific shape, a trough that dips down and then rises back up, over a range of about 20 megahertz. The standard approach is to fit a smooth polynomial to the foreground, subtract it, and look for the residual trough. But if your polynomial is too flexible, it absorbs the signal along with the foreground. And if it is not flexible enough, foreground residuals can create spurious features that mimic a signal. The entire measurement lives on the knife edge between overfitting and underfitting, and the margin of safety is microscopically narrow. Bowman and his team used a 5-term polynomial in the logarithm of frequency to model the foreground, a choice that was carefully motivated by simulations and systematic tests, but that later became one of the central targets of criticism. Their antenna, a small ground plane, roughly 5 meters on a side, with a blade dipole above it, sat directly on the desert soil of the Murchison Shire. The soil's electrical properties, which vary with moisture content and mineral composition, affect the antenna's beam pattern, which in turn affects how the instrument sees the sky, which in turn affects the foreground subtraction. Measuring the soil properties precisely enough to model the beam at the required accuracy is itself a multi-year engineering challenge. Every component of the instrument, the cables, the connectors, the low-noise amplifiers, the analog-to-digital converter, the ground plane, the soil beneath it, the ionosphere above it, introduces systematic uncertainties that must be characterized and removed to levels of precision that would make most experimental physicists sweat. And Bowman did all of it. Over roughly 10 years of sustained effort, from his first EDGES paper in 2010 to the deployment of EDGES 2 with its improved antenna in 2015, he and his team drove the systematic uncertainties down to levels no other 21-centimeter experiment had achieved. He published calibration papers, beam pattern papers, foreground modeling papers, the kind of work that does not make headlines, but that makes a measurement trustworthy. And in February 2018, he reported a detection. And Bowman heard something. In February 2018, the team published in Nature, volume 555, pages 67 through 70. They reported the detection of an absorption profile centered at 78 megahertz, consistent with redshift approximately 17, with a flattened shape that was wider and deeper than standard models predicted. The depth of the trough was approximately 500 millikelvin, roughly 2.2 times the standard model ceiling of 230 millikelvin. Think about what that number means physically. The hydrogen gas at cosmic dawn was absorbing more radiation than the standard model says it should have been capable of absorbing. The absorption depth depends on the contrast between the gas temperature and the background radiation temperature. To make the absorption deeper, you can either make the gas colder or make the background brighter. Standard cosmology has the gas temperature pinned down by the adiabatic cooling of an expanding universe and the CMB temperature determined by COBE to exquisite precision. Both are known quantities. There is no room in the standard model for a 500 millikelvin trough. Two exotic possibilities emerged immediately. The first was proposed by Renan Barkana at Tel Aviv University, published in Nature the same week as the EDGES result. He suggested that dark matter particles might have been scattering off hydrogen atoms in the early universe, extracting heat from the gas, cooling it below its standard model temperature, and thereby deepening the absorption trough. This required dark matter particles lighter than a few giga-electron volts and a specific velocity-dependent scattering cross-section. It was exotic, but it was potentially testable. The second possibility pointed directly at the space raw. If the radio background at cosmic dawn was brighter than the CMB alone, if there were an additional source of radio photons at redshift 17, beyond what the standard model accounts for, then the contrast between the gas temperature and the background would be enhanced, and the absorption trough would be deeper than predicted. An excess radio background at cosmic dawn is exactly what you would expect if the Aracade 2 excess, or some fraction of it, originated in the early universe. The two anomalies, separated by a decade and detected by completely different instruments at completely different frequencies, appeared to be pieces of the same puzzle. The papers proliferated. Andrea Ewell Weiss, together with Su Ching Chang, Joseph Lazio, Olivier Dor, Michael Seifert from the Aracade 2 team itself, and Raoul Monsalve, published in the Astrophysical Journal, Volume 868, Article 63, a detailed model showing how accreting intermediate mass black holes at high redshift could produce both the LWA and Aracade radio excess and the EDGS absorption depth simultaneously. The black holes would emit radio radiation through jets and accretion disk processes, adding to the CMB as an excess radio background that would enhance 21 centimeter absorption and accumulate over cosmic time into the excess observed today. Feng and Holder built a complementary model. Fialkov and Barkana explored the parameter space in a series of papers. Mirusha and Ferlanetto mapped the constraints. Race, Fialkov, and Barkana performed detailed simulations. For roughly 3 years, the space raw had something it had never had before: a context, a connection, a possible mechanism. The signal was no longer floating in isolation. It was linked to the most exciting measurement in 21 centimeter cosmology, and through that link, to the physics of the first stars, the first black holes, and the dawn of structure in the universe. The two anomalies reinforced each other. The edge's depth needed an excess radio background. The Aracade excess needed a mechanism at high redshift. Each was the other's missing piece. Then the replication failed, and the person who killed it was someone we have already met. SARAS 3, the shaped antenna measurement of the background radio spectrum, was designed at the Raman Research Institute in Bangalore by a team led by Saurabh Singh and Ravi Subramanian. That name again, Subramanian, the same physicist who in 2013 had argued that the Aracade 2 excess was a galactic artifact. Now, 9 years later, he was leading the experiment that would challenge the one result that might have vindicated the cosmic interpretation of the signal. I want you to appreciate the position Subramanian occupies in this story. He appears twice, and both times he is the skeptic, the person whose work complicates the narrative rather than resolving it. First, he challenged the signal's reality. Now he challenged the one observation that might have explained it. He is not a villain. He is something more interesting than that. He is a careful scientist whose instinct is always to question and whose questions keep turning out to matter. SARAS 3 used a fundamentally different antenna design from edges. Instead of a blade dipole over a metal ground plane in a desert, it used a fat, cone-shaped monopole antenna deployed on the surface of water, specifically Dandeganahalli Lake and the Sharavati backwaters in southern India. Water provides a smooth, electrically uniform ground plane that reduces the systematic errors caused by ground reflections, soil moisture variations, and impedance mismatches that plague land-based antennas. It was a clever engineering choice, and the result was published in Nature Astronomy, Volume 6, pages 607 through 617, in March 2022. SARAS 3 did not detect the edge's signal. They fitted the edge's absorption profile to their data and found that the best fitting amplitude was consistent with 0. They rejected the edge's profile at 95.3% confidence. The concerns about edges had been accumulating for years before SARAS 3 published. In 2018, the same year as the original EDIS's result. Hills, Kulkarni, Meerberg, and Puchwain published a critique in Nature, questioning whether the 5-term polynomial that edges used to model the galactic foreground was sufficiently flexible to capture the true foreground shape without absorbing part of the cosmological signal, or, conversely, manufacturing a spurious signal from foreground residuals. In 2019, Bradley and colleagues identified additional systematic uncertainties. Singh and Subramanian published their own detailed analysis, also in 2019, in the Astrophysical Journal, Volume 880, Article 26. And then, in 2025, the most definitive reanalysis to date appeared. Cang, Messenger, Murray, Brightman, Chin, and Trotter, published in Astronomy and Astrophysics, Volume 698, Article A152. Instead of fitting the edges data with the original phenomenological model, a flattened Gaussian absorption profile against a polynomial foreground, they forward modeled the data using physically motivated foreground and signal models. Their conclusion was stated without hedging. The presence of a cosmic 21 centimeter signal with a non-standard depth, they wrote, is decisively disfavored. The word decisively is not a word that appears casually in the refereed astrophysics literature. It means they did not merely fail to detect the signal. It means the data actively reject it. The edges result is not dead in the way that a retracted paper is dead. Bowman's team has not retracted. They stand by their analysis. They are deploying EDIGES 3, the successor instrument, which has already been tested at multiple sites and is currently operating in Western Australia, but the independent replication by SARAS 3 failed. The independent reanalysis by Cang et al. Found no signal. The burden of evidence has shifted, and the cosmic dawn connection to the space raw, the one link that might have given the excess a mechanism and an epoch, is increasingly treated as dissolved. I want to sit with the human dimension of this for a moment, because I think it reveals something important about the difference between how science looks from the outside and how it feels from the inside. Alan Kogut built an instrument to hear the first stars, the most precisely calibrated radio instrument in human history. Submerged in liquid helium, launched on a balloon to the edge of space, pointed at the quietest patch of the sky. What he heard was a roar that drowned out the signal he was looking for. A decade later, Judd Bowman built a different instrument in a different desert, at a different frequency, for the same purpose, to hear the first stars. What he heard was an absorption signal that was deeper than it should have been, a result that might have been the fingerprint of the same roar that confounded Kogut. And then it turned out that what Bowman heard was probably not real. 2 physicists, 2 decades, 2 instruments, both searching for the same faint whisper from the first light in the universe, both confounded. Neither of them, as of today, has heard the first stars. That is not a failure of science. That is science working exactly as it should, finding unexpected signals, testing them, subjecting them to independent replication, and accepting the result even when the result is disappointing. But it leaves the space raw exactly where it started, alone, confirmed by Arrowcade 2 and LWA1, unexplained by any mechanism in the literature, stripped of its most exciting potential connection to early universe physics. And here is where it gets worse, because with the edges connection fading, the excess has lost its only potential anchor in cosmic history. And that loss is not just disappointing, it is scientifically disabling. Let me explain why. The Arrowcade 2 signal is what physicists call an integrated quantity. It is the sum of all the radio photons arriving at Earth from every direction, produced by every source along the entire line of sight, accumulated over the full history of the universe. It is like measuring the total amount of light entering a room without being able to tell which lamp is producing the excess glow. The total flux tells you how much extra light there is. It does not tell you where it originated or when it was produced. If the edge's result had held up, it would have provided exactly this kind of localizing information. An anomalously deep absorption trough at redshift 17 would have meant the excess radio background was already present at that epoch, roughly 180 million years after the Big Bang. That would have constrained the source to the first few 100 million years of cosmic history, a specific era when specific astrophysical processes were operating. You could then ask, what was happening in the universe at that time that might produce the excess? Accreting primordial black holes, population, 3 stellar remnants, exotic dark matter interactions in the dense early cosmos. The early universe is strange enough to host strange explanations. But without the edge's anchor, the excess could have been produced at any redshift, any era, any epoch in the 13.8 billion year history of the cosmos. The photons arriving at Earth today could have been emitted 10 billion years ago, when galaxies were assembling rapidly and the universe was dense with star formation. Or they could have been emitted 2 billion years ago in the relatively quiet recent universe. Or they could be produced continuously, right now, by something that operates at all epochs simultaneously. We simply cannot tell. The signal is everywhere in space because it is isotropic. It is everywhere in time because it is integrated. It is, in the most literal sense, a mystery without a crime scene. A forensic investigator reconstructing an event needs 2 things above all: a where and a when. The space raw provides neither. Every handle you would normally grab to pull the mystery apart, position, distance, redshift, counterpart, spectral identification with a known source class, is missing. The signal specifies what kind of physics is producing it: synchrotron radiation with a definite spectral index, but refuses to specify where, when, or from what. Let me tell you now about the people who have refused to give up, because this part of the story is quietly important for understanding how unsolved problems persist in science. Jack Single was a graduate student at Stanford when he joined the Arcade 2 team. His job was the nuts and bolts. The instrument paper, Single et al., 2011, Astrophysical Journal Volume 730, Article 138, describes in exhaustive detail how the calibrator cones were machined, how the radiometer switching cycle operated, how the data were reduced. This is not glamorous work. It is the work that makes a measurement trustworthy. He was a young scientist building the foundation of someone else's instrument. Now he is a professor of physics at the University of Richmond in Virginia, and he has become the person who holds the space raw problem together. He organized the first radio synchrotron background workshop in Richmond in July 2017. He organized the second in Barolo, Italy in June 2022. He is the lead author of both workshop summary reports, published in the publications of the Astronomical Society of the Pacific. He has published more papers on the radio excess than anyone else alive. He did not choose this specialization in the way that a young physicist chooses a hot topic in order to advance their career. This is not a hot topic. There are no large collaborations competing for the answer. There are no billion-dollar instruments being built to solve it. There is Single and a handful of other specialists scattered across 3 continents, and 2 workshops in 19 years, and a growing stack of papers that keep eliminating explanations without finding one that works. I find Single's trajectory as a scientist quietly instructive. In astrophysics, the standard career path is to work on problems where progress is measurable, where you can publish papers that report a discovery, a confirmation, a new constraint that narrows the parameter space toward a known target. The space raw is the opposite of that. It is a problem where progress consists of ruling things out, of demonstrating that another proposed explanation fails, of confirming yet again that the signal is there and still unexplained. Singel's career has been defined by a signal he cannot explain, by a problem that he carries not because it is rewarding in the way that solved problems are rewarding, but because someone has to carry it and nobody else will. In his 2023 workshop report, published in PASP, he lists the tests that have been performed, the constraints that have been set, the mechanisms that have been excluded, with the careful, systematic patience of a detective who knows the case is cold but refuses to close the file. And I want you to notice something about the two workshop locations: Richmond, Virginia in 2017, and Barolo, Italy in 2022. Richmond is where Singel works. He organized the first workshop in his own backyard, at his own university, because nobody else was going to do it. Barolo, in the hills of Piedmont, was selected for the second workshop, presumably because someone needed to gather 24 radio specialists in a room. Again, and Barolo, a small town known for its wine and its medieval castle, was as good a place as any to spend 2 days talking about the loudest unexplained signal in the universe. These were not major conferences. They were not sessions at an AAS meeting or an IAU symposium. They were dedicated workshops, organized by Singel, attended by a few dozen people, addressing a single question. What is this signal, and where does it come from? The fact that the question required its own dedicated workshops, separate from the normal conference circuit, tells you something about how the broader community relates to the problem. It is important enough to warrant its own venue, but not important enough to make the agenda of the big meetings. The Richmond Workshop Report is a document I find remarkable for what it reveals between the lines. The participants included observers from national radio observatories, theorists from universities in the US and Europe, instrumentalists from NASA and JPL, and specialists in galaxy evolution, dark matter, and early universe physics. They spent 2 full days reviewing every aspect of the problem. At the end, they voted on 2 formal propositions. The first was whether the radio monopole level is at or near that reported by Arrowcade 2. The majority agreed that it is. The second was whether the production of this level of radio surface brightness, if confirmed, represents a major outstanding question in astrophysics. That vote was unanimous. Unanimous. A room full of professional astrophysicists, after 2 days of technical presentations and discussion, agreed without a single dissent that the signal is real and constitutes one of the most important open problems in their field. And outside that room, the problem has generated almost no sustained public attention. No full-length documentary before this one has been dedicated to it. Nobody in Congress has asked why the electromagnetic budget of the universe does not balance. The problem is unanimously agreed to be important and almost universally ignored. And here is where I want to talk about something that is not usually said in science content, because it makes people uncomfortable. The allocation of scientific attention is not a meritocracy. It is a market, and markets have preferences. Dark matter has generated enormous institutional investment. Underground detector experiments like XENON, Lux Zeppelin, and Panda X have cost hundreds of millions of dollars. The Large Hadron Collider at CERN, which searches for dark matter particles, among other objectives, cost roughly $10 billion to build and operate. The Euclid Space Telescope, designed to map the effects of dark energy on cosmic structure, cost approximately 1.4 billion euros. These are the problems that attract funding, not necessarily because they are more important than the radio excess, but because they have theoretical frameworks that define what success would look like. The dark matter community knows what it is looking for: a WIMP interaction, a specific recoil energy in a xenon detector. Funders know what they are paying for. The experiment either finds the particle or it sets a new exclusion limit. Both outcomes are publishable. Both advance the field. Both justify the investment. The space raw does not have that luxury. There is no theoretical framework. There is no target particle. There is no predicted signal shape that a new instrument could be optimized to detect or exclude. There is only the excess itself, already measured, already confirmed, already unanimously agreed to represent a major question, and no theory to tell you what to build next. Funding agencies faced with a proposal that says, "We want to measure something we already know exists but cannot explain," will ask a reasonable bureaucratic question. What will the instrument tell you? And the honest answer, the answer Kogut would have to give is, we do not know what it will tell us, because we do not know what is causing the signal. And until we know what is causing it, we cannot predict what additional measurements will reveal. That is scientifically honest and bureaucratically fatal. This is not a conspiracy. I want to be clear about that, because conspiracy framing is lazy and it is wrong. Nobody is suppressing the space raw. It is published in the Astrophysical Journal. It is indexed on NASA's Astrophysics data system. Anyone with an internet connection can read every paper. The workshops are open. The summary reports are freely available on Arxiv. The problem is not suppression. The problem is structural. The incentive systems that allocate attention, funding, telescope time, graduate student positions, postdoctoral fellowships, and faculty hires in astrophysics are optimized for problems with established theoretical frameworks, problems where the community can define success criteria in advance and measure progress against them. Problems without frameworks do not fit the template. They receive attention from individuals, from small groups, from the Jack Singles of the world who refuse to let go of a problem that chose them decades ago. But they do not receive institutional priority. They do not generate mission announcements, or decadal survey rankings, or multi-institution collaborations with acronyms and websites and press offices. And so the loudest unexplained signal in the history of radio astronomy sits in the literature, confirmed and unresolved, waiting for either a theoretical breakthrough or a champion with enough institutional weight to force the question onto the agenda. It has been waiting for 19 years, and the quiet irony is that if someone does eventually explain it, if some theorist somewhere writes a paper that provides the mechanism, the explanation will almost certainly be treated as a major discovery. The Nobel Committee will take notice. The press releases will flow, and everyone will wonder why nobody paid attention sooner. That is how these stories always end. First, it is impossible. Then when someone does it, it was obvious all along. The one thing it can never be is important while it is still unsolved. You should be asking yourself, why? And the answer, I think, is uncomfortable but instructive. The space raw does not fit any of the narratives that drive public interest in physics. It is not about time travel. It is not about parallel universes. It is not about whether consciousness collapses the wave function. It is not about black holes devouring stars or about the accelerating expansion of the cosmos. It is about the plumbing, the accounting, the energy budget, photon bookkeeping. And photon bookkeeping does not make headlines, does not generate viral videos, does not inspire screenwriters. But here is the thing about plumbing. nobody thinks about it until the toilet explodes. And the history of physics is full of explosions that started as plumbing problems. The ultraviolet catastrophe at the end of the 19th century was a plumbing problem. The classical theory of blackbody radiation predicted that a hot object should emit infinite energy at short wavelengths. This was not an exotic prediction about time travel or consciousness. It was a prediction about how much light a glowing piece of metal should produce. A bookkeeping problem, an energy budget that did not balance, and resolving it required Max Planck to introduce the quantum hypothesis in 1900, which dismantled classical physics and launched the most profound revolution in the history of science. The perihelion precession of Mercury was a plumbing problem. Mercury's orbit precessed at a rate 43 arcseconds per century, faster than Newtonian gravity predicted. 43 arcseconds. That is roughly 1/100th of a degree. An accounting discrepancy so small you could be forgiven for ignoring it. And resolving it required Einstein to replace Newtonian gravity with general relativity, which rewrote humanity's understanding of space, time, and gravity. The missing solar neutrinos were a plumbing problem. Physicists calculated how many neutrinos the sun should produce through nuclear fusion, built a detector to count them, and found only 1/3 of the expected number. A factor of 3 discrepancy in a particle count. A census that did not balance, and resolving it required the discovery of neutrino oscillations, which proved that neutrinos have mass, a fact that the standard model of particle physics does not predict and still does not fully explain. The space raw is a plumbing problem. The radio energy budget does not balance by a factor of 5 to 6. That factor is larger than the solar neutrino deficit, larger than the Mercury precession anomaly, and comparable in scale to the ultraviolet catastrophe. And every one of those plumbing problems turned out to be a crack in the foundations of physics. Not because the discrepancy was dramatic, because the discrepancy was precise, because it was repeatable, because it resisted every attempt to explain it within the existing framework. And because, in the end, the only way to close the books was to rewrite the rules. The 5 years between the two workshops saw a subtle shift in institutional language that I find telling. The 2017 report described the excess as by far the least well understood photon background. By 2022, the by far was gone. The excess was simply the least well understood electromagnetic background. A small change, a softening, the language of acclimatization. The community has not solved the problem. It has learned to live with it. And the way institutions live with unsolved problems is by lowering the rhetorical temperature until the problem no longer sounds urgent, even when the data have not changed. The Barolo workshop concluded with a set of priorities for moving forward. They are methodical, cautious, and specific, which is to say they are the language of a community that has exhausted its quick answers and is settling in for a long campaign. The priorities include searching for the radio Sunyaev-Zeldovich effect through galaxy clusters. This is a specific observational test. If the radio excess is truly cosmological, present at all redshifts, then galaxy clusters should cast shadows in the radio excess, just as they cast shadows in the CMB, through the thermal Sunyaev-Zeldovich effect. Detecting a radio SEZ decrement would prove the excess is cosmological and date it to before the cluster formed. The priorities also include cross-correlation analyses, searching for statistical associations between the radio sky and traces of large-scale structure like galaxy density maps, infrared backgrounds, and gamma-ray maps. And they include supporting the completion of a new, absolutely calibrated sky map at 310 MHz, which would provide the cleanest measurement yet of the excess's spectral behavior in a frequency range where the signal is strong and the galactic foreground is well characterized. These are all sensible steps. They are all doable with existing or near-future instruments, and none of them individually will solve the problem. They will constrain it. They will narrow the space of possible answers. But without a theoretical framework, without even a plausible mechanism that is not already ruled out, the constraints accumulate without converging. You can draw a tighter and tighter box around the mystery without identifying what is inside it. And then there is Fixsen, the primordial inflation explorer. This is Alan Kogut's successor instrument. His response to the question that Arcade 2 asked and could not answer. Fixsen is designed as an orbital mission carrying a cryogenic Fourier transform spectrometer with 300 spectral channels covering frequencies from 28 GHz to 6 THz, with roughly 1,000 times the sensitivity of COBE's SARAS instrument. SARAS is the instrument that produced Fixsen's CMB blackbody spectrum, the most perfect blackbody in nature. Fixsen would be FIRAS multiplied by 1,000, measuring the entire electromagnetic spectrum of the universe from radio through far infrared with absolute calibration, simultaneously and precisely. It would not just measure the radio excess. It would map every photon background in the sky, determine the exact spectral shape of each, and potentially identify spatial structure in the excess that could point toward a source mechanism. It would also measure the spectral distortions of the CMB predicted by decades of theoretical work, constrain dark matter annihilation, probe the epoch of reionization, and test models of cosmic inflation. It would do more cosmology per dollar than almost any mission ever proposed. Kogut submitted the Fixsen concept to NASA's 2024 Astrophysics Probes competition. 8 proposals were submitted. 2 were selected for $5 million 12-month concept studies in October 2024, AXS and Prima, with a final single mission selection planned for 2026 and launch targeted for 2032. AXS was subsequently disqualified, leaving Prima as the sole finalist. Fixsen was not among the 2 selected. It remains a concept, without a launch date, without a timeline. I find something quietly devastating about this. The man who helped measure the temperature of the universe to 4 decimal places with COBE, whose balloon instrument uncovered the loudest unexplained signal in the history of radio astronomy, who designed the one space mission capable of definitively characterizing that signal and placing it in the context of every other photon background in the cosmos. He cannot get it funded, not because the science is weak. The science was unanimously agreed by a room full of specialists to represent a major outstanding question, but because the politics of NASA mission selection favor topics with established theoretical frameworks, topics where the community knows what it is looking for and can define success criteria in advance. The Space Raw does not have a theoretical framework. It has a signal, and funding agencies do not like funding signals without frameworks because they do not know what success would look like. There is a pattern here, and it has nothing to do with the quality of the physics. Meanwhile, the instruments that are deploying are aimed at a related but different target, the cosmic dawn measurement that EDGES attempted and probably failed. EDGES 3, Bowman's successor experiment, has been on multiple deployments over the past 4 years, to Oregon, to Devon Island in the Canadian Arctic, to Adak Island in the Aleutian Chain, and as of 2025, as described in a paper by Capallo and colleagues on ArcSiv in August 2025, EDGES 3 is installed and taking data in the outback of Western Australia, the same desert where the original EDGES operated, REACH, the radio experiment for the analysis of cosmic hydrogen, led by a team at the University of Cambridge, is operating in the Karoo Desert of South Africa. MIST, the mapper of the IGM spin temperature, based at McGill University in Montreal, has been deployed to Marion Island in the subantarctic and to sites in the Canadian high Arctic. Each of these experiments is attempting the measurement that EDGES claimed and SARAS-3 rejected. The detection of the sky averaged 21 centimeter absorption signal from the epoch when the first stars turned on. If any of them detect a genuine absorption signal with a depth significantly exceeding the standard model prediction of 230 millikelvin, the connection to the space raw could resurrect. An excess radio background at cosmic dawn would deepen the trough, and the Arcade excess would have a mechanism and an epoch. But the evidence from SARAS-3 and Cang et al. Suggests the EDGES signal was not real, and if the actual cosmic dawn absorption turns out to be consistent with the standard model prediction, then the early universe route to explaining the space raw is permanently closed. The excess would have to be produced at lower redshifts in the more recent universe by a mechanism operating in an era we can observe directly. And in that era, every mechanism has already been tried and has already failed. And further out, on a timescale of decades, there is the Square Kilometre Array, the most ambitious radio telescope ever conceived. SKA is being constructed across two sites, one in the Karoo semi-desert of South Africa, hosting 197 dish antennas, each 15 meters in diameter, and one in the Murchison region of Western Australia, hosting 131,072 low-frequency dipole antennas spread across 74 kilometers of desert. When fully operational in the early 2030s, SKA will have a collecting area of roughly 1 square kilometer, making it the most sensitive radio telescope in human history by a factor of roughly 50 compared to current instruments. It will detect radio sources 1,000 times fainter than anything visible to today's surveys. This matters for the space raw because SKA will provide the definitive test of the most conservative remaining hypothesis, that there is a hidden population of ultra-faint sources that Condon's PD analysis missed. If SKA's deep surveys at 1.4 GHz reveal a previously undetected population of radio sources whose integrated emission fills the gap between the known source counts and the Arcade excess, then the mystery dissolves. The boring answer was right all along, just at flux densities below the reach of any previous instrument. The universe is not mysterious. It is merely full of dim radio sources. But if SKA does not find them, and I want to be transparent about why I think this is the more likely outcome, because the PD constraints from Condon already rule out the required population to very high confidence, and because the spectral shape of the excess does not match the spectral properties of any known radio source population at any flux density, then the mystery deepens catastrophically. Because at that point, the faint source loophole, the last refuge of the conservative explanation, closes permanently. And the only remaining options are genuinely exotic, a new class of source, a new physical process, a modification of our understanding of what the universe contains. Either way, SKA will not be fully operational until the early 2030s. The space raw will have been sitting in the literature, confirmed and unexplained, for a quarter of a century before the instrument most capable of testing its most fundamental proposed solution comes online. 25 years. For a signal that is currently filling the room you are sitting in, that is passing through you at the speed of light. That has been doing so for your entire life, and for the entire life of every human being who has ever lived, and possibly for the entire life of the universe. And we did not know it was there until 2006. And we still do not know what it is. There is something about this that I find difficult to articulate, a feeling that sits somewhere between frustration and awe. We live in an era of extraordinary scientific achievement. We have mapped the cosmic microwave background to millionths of a degree. We have detected gravitational waves from colliding neutron stars. We have imaged the event horizon of a supermassive black hole. We have measured the age of the universe to a precision of less than 1%. And yet, we cannot account for the total radio emission of the cosmos, the most basic measurement you can make. How bright is the sky produces a number we cannot explain. Not because we have not looked, because we have looked and looked and looked, and the answer is not in any of the places we know how to look. And that brings me to where I have been trying to get this entire time. The implication, not the scientific details, which I have now given you in full. The implication for what this means about the universe you are sitting in right now. We have an energy budget for the universe. It is one of the foundational projects of observational cosmology. You count the photons at every frequency across the electromagnetic spectrum. You trace them back to their sources. You add up the contributions from every known class of radiating object, and you verify that the total production matches the total observation. For the cosmic microwave background, the budget closes. The CMB is a black body at 2.725 Kelvin, produced at recombination 380,000 years after the Big Bang, and it matches predictions to 50 parts per million. For the cosmic infrared background, the budget closes. It is produced by dust-enshrouded star formation, an active galactic nuclei, and the integrated emission from galaxy surveys matches the observed background within the uncertainties. For the extragalactic background light at optical wavelengths, the budget closes. For the cosmic X-ray background, the budget closes, dominated by active galactic nuclei. For the gamma-ray background, the budget closes, dominated by blazars and other gamma-ray sources. Every electromagnetic background in the universe has been accounted for, except one. The radio background does not close. It is off by a factor of 5 to 6. The measured brightness exceeds the integrated contribution of every known radio source by roughly 400%. And when Singhal convened a room full of specialists and asked them whether this represents a major outstanding question in astrophysics, the answer was unanimous. And here is the implication that I have been building towards since the beginning of this script, and I need you to understand why it is larger than it appears at first glance. We already knew that 95% of the universe is invisible. Dark matter constitutes roughly 27% of the total mass energy content of the universe. Dark energy constitutes roughly 68%. Together, they account for 95% of everything, and we cannot see either of them, cannot detect them directly, cannot tell you what they are made of, cannot produce them in a laboratory. We have been living with this fact for decades. 95% of the universe is dark, unknown, beyond our current understanding, and we have consoled ourselves quietly with the observation that at least the remaining 5%, the ordinary baryonic matter made of protons and neutrons and electrons, the stuff that shines, the stuff we are made of, was understood. We could see it, measure it, catalog it, photograph it. We could count its photons, and the photons added up. The dark universe was the mystery. The bright universe was the solved problem. The Space Raw says the bright universe is not solved. Within the 5% that radiates, within the electromagnetic spectrum, within the one domain where counting photons was supposed to be a closed book, there is something enormous and unidentified, something producing 5 to 6 times more radio energy than every known source in the observable universe combined. And it is not dark matter, because dark matter does not radiate. It is not dark energy, because dark energy has no electromagnetic signature. It is something that actively emits real photons at radio frequencies, real synchrotron radiation, requiring real relativistic electrons in real magnetic fields, accelerated by a real mechanism. And those ingredients, every single one of them, do not exist in any model, any simulation, any catalogue, or any survey of the known universe. We are not just failing to see 95% of the universe, we are failing to hear what the remaining 5% is actually doing. And this is the part I still do not know how to process. Because think about what it means for the project of understanding the cosmos. We built telescopes, we catalogued billions of galaxies, we mapped the cosmic microwave background to millionths of a degree. We measured the expansion rate of space. We detected gravitational waves from merging black holes a billion light years away. We photographed the shadow of a supermassive black hole in the galaxy M87. We built particle accelerators that recreate conditions a trillionth of a second after the Big Bang. And after all of that, after centuries of accumulating observations and decades of precision cosmology, we still cannot account for the total radio output of the universe, not approximately, not within a factor of 2. The radio books are off by a factor of 5 to 6. The universe is radiating, and we do not know what is doing the radiating. This is not like dark matter, where we infer the presence of invisible mass from its gravitational effects on visible matter. The space raw is not invisible. It is the opposite of invisible. It is electromagnetic radiation. Photons, the thing we are best at detecting. Radio photons have been detected by human instruments since Carl Jansky first heard the Milky Way's radio hiss in 1932, 94 years ago. We have been building bigger, more sensitive, more precisely calibrated radio telescopes for nearly a century. And the thing that confounds us now is not something hiding from those telescopes. It is something those telescopes can see perfectly well. The photons are right there. They are arriving at Earth at this moment. Every radio telescope on the planet is bathed in them. The signal is not subtle. It is not elusive. It is the loudest, unexplained phenomenon in the electromagnetic universe. And it is not going away. It will not be resolved by a recalibration. It will not dissolve when we build a bigger telescope. The bigger and more sensitive our instruments get, the more precisely they measure the same discrepancy. The more precisely we count the known sources, the more precisely we confirm that the known sources do not add up. The gap does not shrink with better data. It calcifies. It becomes more certain, more precisely measured, more stubbornly present. There is something in the universe that our physics does not contain. Something that radiates, something that fills every direction of the sky equally. Something whose spectral fingerprint matches no known mechanism. And the fact that we have been looking at it for 19 years and cannot identify it should not make you comfortable. It should make you profoundly uncomfortable, because the electromagnetic spectrum was supposed to be the one place where we had the answers, the one domain where photon counting worked, the one piece of the cosmic puzzle that was already solved. And it is not solved. The piece does not fit, and nobody knows what shape it is supposed to be. I keep returning to the image of that July night in 2006. The balloon rising from Palestine, Texas, carrying its liquid helium dewar into the stratosphere. The instrument designed with decades of COBE heritage to achieve the most precise, absolute radio measurement ever made. the team expecting to hear the faint thermal glow of the first generation of stars, the population 3 stars, the primordial furnaces that fused hydrogen and helium into the first heavy elements and began the long chain of nuclear synthesis that eventually produced carbon, nitrogen, oxygen, iron, the atoms that your bones are made of, the atoms that your blood carries. Every heavy atom in your body was forged inside a star. And the earliest of those stars, the ones that started the process, left a faint radio signature in the cosmic background, a thermal echo of the moment the universe first learned to shine. Kogut built Arcade 2 to hear that echo. He never heard it. The space roar drowned it out. The first stars tried to leave a message in the radio sky, a faint thermal whisper encoding when they ignited, how bright they burned, how they changed the dark cosmos around them. And something else, something we cannot identify, something that does not exist in any model of the universe we have ever built, is radiating so loudly over the same frequencies that the message is inaudible. We are trying to listen to the birth cry of light itself, the moment the universe stopped being dark, and something is shouting over it. Something nobody put there, something that does not correspond to any known object, process, or population in 13.8 billion years of cosmic evolution. Something that has been measured, confirmed by independent instruments, published in the Astrophysical Journal, presented at 2 international workshops, and evaluated against 11 proposed explanations, every one of which has failed. I keep thinking about a question that nobody in the workshops has formally asked, at least not in the published proceedings, because it is the kind of question that sounds naive in a room full of professionals, but that keeps you awake at 3 in the morning if you think about it long enough. What if the signal is not produced by a thing? What if it is not produced by a population of objects we have not found, or a process we have not conceived of, or a particle we have not discovered? What if the signal is a property of the universe itself? What if the vacuum, the empty space between galaxies, the background on which everything else sits, is not electromagnetically silent? What if space itself radiates? I am not proposing this as a theory. There is no published model that makes this work. But I am noting that every explanation that has been tried assumes the excess is produced by something in the universe, some object or process that generates the photons. And every such explanation has failed. The photons are there. The objects are not. At some point, if you keep looking for the source and the source keeps not being there, you have to ask whether the concept of source is the right framework. Maybe the question is not, what is producing this signal? Maybe the question is, what if the universe does not need a source to produce it? That is speculative. I know it is speculative, but the fact that it is the kind of speculation that starts to feel less crazy the more failed explanations you stack up is itself a measure of how deep this problem goes. 19 years, 11 failed mechanisms, 2 workshops, 1 independent confirmation, 0 explanations. The signal is still there. The universe is still loud, and nobody can tell you why. Think about what that means for the next time you walk outside at night and look up at the sky. The stars you see are a tiny fraction of the story. Behind them, beyond them, filling the space between them and the space between the galaxies they belong to, there is a bath of radio energy that outshines them all at radio frequencies. You cannot see it, you cannot hear it without a radio receiver. But it is there, right now, streaming through the atmosphere, through the walls of whatever building you are in, through the screen you are watching this on, through the cells of your body. It has been doing this your entire life. It was doing it the day you were born. It was doing it before humans existed. It may have been doing it since the universe began. And the entire apparatus of modern astrophysics, decades of surveys and telescopes and missions and papers, cannot tell you what it is. You have been bathed in a signal that has no name, no source, and no explanation for as long as you have existed. And you did not know it until right now. That is not a comfortable thought. And it is not supposed to be, because the comfortable version of the universe, the version where we understand the bright part and are working on the dark part, the version where the electromagnetic spectrum is mapped and catalogued and accounted for, that version is wrong. It has been wrong since at least 2006, when a balloon carrying a liquid helium dewar rose above Palestine, Texas, and heard something that nobody can explain. And it may have been wrong for much longer than that. The signal was always there. We just did not have ears precise enough to hear it. And we cannot make it stop, because we do not know what it is. We do not know where it is. We do not know when it started. We do not know if it is getting louder or if it was always this loud and we simply lacked the tools to hear it until Kogut and Fixsen built one precise enough to cut through everything else. What we know is that it is there, that it fills every cubic meter of the observable universe, from the space between galaxy clusters to the room you are sitting in right now, that it is isotropic, that it follows a clean synchrotron power law from 22 megahertz to 10 gigahertz, that it requires real particles producing real energy through a real physical mechanism, and that the measured energy output of every radiating object in the observable universe, every star, every galaxy, every accretion disk, every supernova shock, every magnetar flare, every pulsar magnetosphere, all of it is not enough. The universe is louder than everything in it. That is not a metaphor. It is not poetry. It is a measurement, published, peer-reviewed, independently confirmed, and unexplained for 19 years. And somewhere, at NASA's Goddard Space Flight Center, a physicist named Alan Kogut is still refining the design of the instrument he hopes will one day tell us why. An instrument that may never fly, for a signal that may never be explained, in a universe that, as it turns out, we understood even less than we thought, and we thought we understood almost nothing.